I'm going to talk to you today about cosmic collisions, Comet Shoemaker Levy 9's impact on Jupiter. Before I start, if any time during my talk you have a question, I want you to raise your hand and wave it so I can see you amidst these bright lights, and I will get to you as soon as possible to answer it. I'd like to start off with a slide. Start off with an introduction about the event. Between the dates of July 16th and July 22nd, 1994, a small comet named Comet Shoemaker Levy 9 made astronomical history by impacting into the largest planet in our solar system, Jupiter. This composite slide summarizes the event. Here we have Jupiter just before the collision in May with Io, its moon, transiting it, and then the aftershot just after the last massive collision. And the destruction is noted here at the bottom where you see a number of bruises due to the impacts of Comet Shoemaker Levy 9 here at the bottom. Now, what is most amazing about this event is not that a comet collided with Jupiter. Such impacts have battered planets throughout the solar system and throughout the history of the solar system. What is amazing about this event is that astronomers knew a full 1 year in advance, and they had time to organize a global effort to study this phenomena and prepare for it very well. Two other aspects about this event are unusual. First, the data documenting such a collision event in our solar system is unprecedented. There are just gigabytes and terabytes of data floating on this observation. Now, what might not be so obvious to you all is why isn't one picture like this picture here suitable for learning about the event? Isn't one picture worth 1,000 words? Well, that may be true, but one picture doesn't tell a whole story, and it takes many pictures and lots of spectra to actually delve deeply into the physics of what was occurring during this collision. Now, why should we care about collisions in the solar system? First of all, they're an important fundamental process occurring all the time in the solar system, particularly in the formation of the solar system, and the Earth has had many impacts. Some of them are powerful enough to have, we believe, to have caused mass extinctions. Now, before I talk specifically about the collision event of Comet Shoemaker Levy 9 on Jupiter, I'd like to give you a little bit of background, first on collisions, second on comets, third on Jupiter. Let's first start with collisions. Throughout the history of the solar systems, collisions between bodies has been a continual process. And if you look at any hard surface in our solar system, such as this picture of Mercury taken by the Mariner 10 mission, you can see that it's just riddled with thousands and thousands of craters. And of course, our own moon, the Earth's one natural satellite, is riddled with craters. This is the full moon as we see it from Earth. And then a recent mission to the moon, Clementine, which has mapped the entire surface of the moon, has this nice picture of the far side of the moon where the impact craters are even more obvious. What's the structure of an impact crater? If you could take a slice through any one of those impact craters on the moon or on Mercury, this is what it would look like in a profile view. You have a central depression, the center of which is a lot of compressed and highly heated material and rocks. Underneath is a lot of fractured rock, and surrounding this depression is a large steep crater walls and a large ejecta blanket from which leftover from the explosion having been tossed out of that crater area. Now, the craters that we were seeing on the surface of Moon and Mercury show a very clear historical record of collisions in our solar system. Most of those collisions occurred 3 to 4 billion years ago in the early part of our solar system. Now, surely the Earth, which is just the neighbor of the Moon, had experienced just as many collisions as the Moon. Now, I want to ask you a question now. Maybe you can consult with your neighbor about this. Why do we not see many craters on the surface of the Earth as we do on the Moon? Okay, let's take someone, a lot of good conversation here. How about, see, 1, 2, 3, the fourth row up, third person in a sweater, brown and cream sweater. You and your neighbor? Yeah.
Well,
what do you think?
I thought maybe, because we have a thicker atmosphere and things would burn up.
That's a very good, that is certainly very important. However, there's another process. Let's get it. That's a very important process and why we don't have as many craters. Down in front here.
The weather, the road, changes the geography.
Right, weather erosion is an important one as well. Basically, what we're pointing out here is that the Earth has a lot more complicated environment. You have the atmosphere protecting us from comets. We also have, even if they do hit, the evidence for those comet impacts has been eroded over time by weather erosion. And we also have a lot of volcanic activity and plate tectonics which erase or cover a lot of evidence for the impact craters. Now, even though most of the collisions in the solar system occurred billions of years ago, it's still a continual process, and we still have collisions in the solar system. The Earth, for example, is pelted daily by thousands of interplanetary pebbles, which we see in the form of meteor showers, or random meteors. This is a picture of the Leonids meteor shower. These points in the background are stars, and these streaks here are the streaks from these interplanetary pebbles actually burning up in the Earth's atmosphere, and their lines show the trajectory from which they have entered the Earth's atmosphere. Now, as the young woman pointed out, the Earth's atmosphere actually protects us from a lot of interplanetary debris. In fact, it protects us up to sizes of objects of around 10 meters, so it's about the size of this front room, burn up in the Earth's atmosphere because it's thick enough to do that. Now, larger collisions having to occur. This is a map of the world showing sites of known impact craters. I'm going to show you a picture of this one in the southwest, known as the Arizona Meteor Crater. You can see the central depression, the steep crater walls, and just a faint hit of an ejecta blanket. This crater was produced about 50,000 years ago by about a 60-meter diameter iron-nickel meteorite. Such an event, such a collision event, occurs once or twice every 1,000 years. Now, the danger of such collisions to life can be tremendous. Many geologists believe that a large asteroid collided with the Earth around 65 million years ago, causing mass extinction of the dinosaurs. This geologically important time period is known as the KT event, or the Cretaceous Tertiary Mass Extinction Event. It was 65 million years ago. About 70% of all living species, including the last of the great dinosaurs, expired during this period. Evidence for a comet or an asteroid colliding with the Earth causing this extinction is threefold. One is that there's a rare element, iridium, that is found worldwide in this KT boundary layer. It's about 1 centimeter deep, and it's very rare to find that type of element on the surface of the Earth. It's hidden deep down inside usually. But an impacting asteroid which would carry that type of material could land on the Earth and spread that material around. So that's one piece of evidence. Another piece of evidence is that in that same boundary layer with this iridium, we see a large soot layer. Now, a large impacting asteroid could cause lots of fires, burning things, which could create such a soot layer. And third, we have evidence of a large impact crater deep under the layers of the Earth. Located off the peninsula of Yucatan in Mexico, there is a crater called Chicxulub that's centered sort of right on the edge of the peninsula. And this is some very fancy way geologists have of seeing layers of material underneath the surface of the Earth. And you can see the outline ring of a crater. Now, radioactive dating of these crater layers show that the crater can be dated back to 65 million years ago. So the timing is certainly right And such an impact crater in that area certainly would have caused large tidal wave activities in the regions around the Gulf of Mexico. And they have seen evidences for such tidal wave activity in and around the Gulf area. Now, what type of destruction would a 10-kilometer sized asteroid impact cause? Well, to make a laundry list of it, we have, locally there'd be lots of shock waves in the area, be lots of fires, earthquakes, hurricanes, winds, lots of flying debris, months of darkness and cold temperatures following the incident. It certainly would be a very harsh life indeed, and one can certainly imagine that mass extinctions could occur from such a dramatic event. Now, what causes one size or one collision of an asteroid hitting the Earth causing a crater, like the Arizona meteor crater, and another asteroid impact causing mass carnage and destruction? The answer lies in kinetic energy and the conservation of energy. This slide here just shows schematically a collision of some interplanetary rocket here, which is speeding towards us. It hits the Earth. Kinetic energy is the energy of motion, and it depends on the mass and the velocity of that object. When it hits the Earth, it stops moving. But according to the conservation of energy, all the kinetic energy that that body had gets transferred into destructive energy of heat energy and shock energy that we see here. And it compresses the material under which it lands, and that material bursts out and creates the structure that I was showing you of the crater, where you have the crater walls and the ejecta blanket. So let's just look at how we can quantify, let's see, how we can quantify how much kinetic energy a body has. Kinetic energy, if you want to quantify, is equal to 1/2 times the mass of the object times its velocity squared. So it's a little bit more sensitive to velocity than it is to mass. Now, thought we might do a demonstration together here about kinetic energy and its effects. What I want everyone to do in this room is to take your hands and move them about a shoulder width apart. Maybe not so to hit your neighbor, but hold them shoulder width apart. Now I want you to force them together very quickly in a clapping motion. All right. Wow, what a good sound. Okay, now, afterwards you can feel that your hands smart a bit, right? And that smarting is coming from the fact that you're converting the kinetic energy of your hand motions into heat energy, which is heating the surfaces of your hand. So there you've just had a miniature collision. Now, the more destructive collision events have more mass and more velocity. Here's clapping at the top here. We stand over the side. These are a little bit better pointers here. Okay, on this table here, which I think you all have a copy of, we have the event in the first column. Second column, we have the mass involved in the event. In the third column, we have the velocity of the relative velocity of these masses. And in the fourth column, we have the total energy that comes from these events. Now, clapping, which we did, is a pretty minuscule amount of energy, 0.05 joules. What I want you to know is some of the more deadly types of collisions and kinetic energies. The second event there is a head-on collision of two automobiles, which we know is a very dangerous and certainly kills many people. So we have, you can see that the reason why it's more dangerous is there's more mass and there's more velocity than clapping your hands. Now you get into the larger cases of the Arizona meteor crater, which caused an enormous cavernous crater in the southwestern part of the United States. And then you have Chicxulub, which caused mass extinctions over the entire world. And our topic of today, Comet Shoemaker Levy 9, it had a kinetic energy and a destructive power of around somewhere between the Arizona meteor crater and Chicxulub, and that's because the mass of the fragments was smaller, greatly smaller than the mass of the Chicxulub crater perpetrator. The velocity, however, was very high, and which is the main reason why it was very destructive. And then put into yet another, comparing it to other different types of collisions and other types of energy, I have another comparison chart here between events, some of which I showed in the other graph, the head-on collision, and these final two collisions of Comet Shoemaker Levy 9 and Chicxulub. What I want to point out is some of the other types of energies. A ton of TNT, which is dynamite, is about 5,000 times of a head-on collision of cars. And two other things, the fusion bomb, which are the bombs of which most of the nuclear arsenal of the world are made of, has an enormous amount of destructive power. Not as much destructive power, however, than the US consumes in electric power an entire year, which is this next entry. And then when you get to comet collisions of large interplanetary material with a surface like the Earth or Jupiter, you're talking about even greater amounts of power and destructive energy. Comet Shoemaker Levy 9's fragment released more destructive energy in the atmosphere of Jupiter than the world's entire nuclear arsenal, and Chicxulub was even greater than that. So I hope I piqued your interest in learning a little bit more about collisions. I'd like to now talk about comets and what comets are. First of all, what are comets made of? We have here is a dirty snowball, and comets are basically dirty snowballs traveling around in interplanetary space. They're loose conglomerations of dust particles like silicates or automobiles, or carbonaceous dust grains like this automobile soot that's on this dirty snowball. And then they're also mixed in there are ices, such like the water ice we have in these snowballs, but also other types of ices like ammonia and methane and formaldehyde. So this picture of this dirty snowball you can extrapolate in terms of the content and also in terms of the size. Comet-sized dirty snowballs range from about the size of this room to about the size of the U of I campus. They get to be very big. And certainly Comet Shoemaker Levy 9 was a very big dirty snowball. Okay. We see comets. If you look at this picture here, this is a picture of Comet Halley as it passed through near the Earth in 1986. What happens as a comet approaches the sun is that the ice in this dirty snowball heats up and sublimes off the snowball, and it loosens the dust as well. And this is a picture close up of the very head of the comet of Halley, and it's known as the coma of a comet. What happens is that dust and that gas freely expands off the comet into the relative vacuum of interplanetary space. And the comet has little self-gravity. It's pretty puny in mass compared to objects, for example, like the Earth, that can hold an atmosphere on top of it. So this gas and dust just expands freely out, never to return, and the sun's radiation pushes that gas and dust away from the sun, forming two tails. Here's the comet's coma. The sun's up here somewhere, and we have a bluish tail known as a gas tail, and we have a dust tail, which is a little bit more yellowish. Now, I just wanted to have a summary cartoon of the comet. What does a comet look like? This is my comet cartoon. So inside the nucleus is that dirty snowball I was talking about. The coma is that large halo. These comas can get really, really big. They can get up to a size of a degree in the sky, which is much larger than the full moon, so they're very obvious to see. And then we have the two tails, the plasma tail, which is a hot gas tail, and the dust tail. Now, if you, this is a picture of Comet Halley's orbit around the sun during its last pass. I wanted to point out again that the tail's pointing away from the sun, not behind it in its trajectory around the sun. And also a very interesting investigation of comets was carried out when a spacecraft Giotto was flown to encounter with Comet Halley, and in the process accumulating a lot of data about compositions of comets and what it looked like when you got really close inside to a comet. And this is a picture of the nucleus of Comet Halley just before the Giotto spacecraft basically disintegrated in its encounter with Halley. These bright patches here is that ice subliming off and heating up and expanding off the comet nucleus. And these dark parts are more of that dusty region that you see in comets. Now, how are comets discovered? Maybe you'd like to go out and try to discover some comets. They're a lot of fun to go look for. Comets are usually discovered by amateurs because particularly disciplined amateurs that go out basically every week looking for things that are unusual in the sky. And in fact, that's how Comet Shoemaker Levy 9 was discovered. Where do comets come from? From, we believe, two reservoirs. First, we have something called the Oort cloud, which is enormous in size, starting way out on the edges of the solar system beyond Pluto. And it's basically a cloud from which occasionally comets will come in. A second reservoir of comets known as the Kuiper belt, from which we believe Comet Shoemaker Levy 9 originally started from, are much closer. They have shorter periods. Kuiper belt comets have periods of around 5 to 7 years. That is, they return to the inner solar system where we can see them about every 5 to 7 years. And their aphelion, that is their distance furthest away from the sun, is out in the gas giants regions, such as Neptune, Uranus, and Saturn. Now, lots of these massive giants have a lot of impact or influence on how the comets travel around. In particular, Jupiter, the largest, most massive planet in the solar system. Planetary orbits and comet orbits are determined by the gravitational fields, and the sun, being the most massive, controls most of their motions. However, massive planets like Jupiter can have an effect, and this was particularly the case in Comet Shoemaker Levy 9. Okay, so now I've introduced you briefly to comets and collisions. I want to talk about the victim in this case. Tell you a little bit about Jupiter. It's a picture of Jupiter again. This was shortly before it was bombarded by Comet Shoemaker Levy 9. Some basic statistics about Jupiter. Going down this list, first of all, it's about 5 astronomical units away from the sun. The Earth is 1 astronomical unit, so it's about 5 times as far away from the sun as we are. Its mass is about 300 times the mass of the Earth, and it is the most massive planet in our solar system. And we know the mass of Jupiter because we watched the orbits of its moons, such as Io, orbiting around it, and we can determine the gravitational energy and force of Jupiter and know its mass, since mass is what dominates the gravitational force. Now, what about the size of Jupiter? Jupiter is about 11 times the size of the Earth. Its radius is roughly spherical. Its radius is about 11.2 times the size of the Earth's radius. Its mean density, however, is very much smaller than the Earth's. What the mean density, how we calculate mean density is to take the total mass of the planet, we divide by its volume. That's what its mean density is. It's a little bit higher than that of water, and it's much less than the Earth's, which is 5.4 grams per cubic centimeter. And what this means is that it's a little bit more fluffier consistency than the Earth is. Now, Jupiter has a very fast rotation rate, the Earth takes 24 hours to rotate. Jupiter takes a little less than 10 hours, which we'll find out is actually very crucial for the astronomers who are studying this event. Jupiter has an enormous magnetic field, about 14 times that of the Earth. We find that this magnetic field also interacted with this comet collision. Now, Jupiter has a whole entourage. It's almost a miniature solar system of objects. It has 16 moons, 4 of which were discovered by Galileo in the 1600s. The 4 Galilean moons are Io, Europa, Ganymede, and Callisto. And discovered by the Voyager missions, a very thin pair of rings near Jupiter. This is a mosaic of pictures. This is Jupiter blotted out, so you can actually see the much fainter rings that are circling around Jupiter. And a few other interesting things about Jupiter. Of course, its trademark red spot, which is an enormous storm that's been going on for at least 300 years. It's about, the storm itself is huge. It's about twice the size of the Earth. You can fit 2 Earths in there. And recently, the Galileo space probe was just deposited into the atmosphere of Jupiter. At least part of the probe was. Most of the probe is still orbiting around Jupiter, and it's just started its mission to study Jupiter over several years to learn more about Jupiter as a planet. This comet was a real serendipitous event because we got to even learn more about it than we could just with the Galileo space probe. Okay, what about the structure of Jupiter? So this is a topic that is addressed both with the comet collision and with Galileo. What do we know about Jupiter? We know very little hard facts, but we have what we do know about it. We try to interpret the structure of Jupiter. First of all, about its interior. This is based on models which are constrained purely by the total mass of Jupiter. But what we think is happening inside of Jupiter is that we have a rocky core that is about maybe 12 Earth masses. And it's rock in the sense it's a jumble of silicates and carbons and irons. And we have an ice layer around the outer part of the rock. And then surrounding that is a very thick layer of liquid metallic hydrogen. Nothing that we have made in the laboratories here. You need enormous pressures to do that. We have liquid metallic hydrogen, and then above that we have a layer of liquid molecular hydrogen, and then above that are the gaseous clouds and atmosphere of Jupiter. Now, up here in this slide, I have a description of the atmosphere, which is actually very important in understanding the collision process, because the comet, as it turns out, yes?
Oh, I have a question. With really high pressure and the gravity and everything, why is the density so light? Is it just the materials or the three atoms?
Yes. It's the materials. That's a very good question. Certainly, as you go in the center of any planet or any star, the densities and temperatures increase dramatically as you get to the core. However, the mass of something depends a lot on its composition and then how much of it has of that material. In the case of Jupiter, you can see that most of it's made of hydrogen and helium, which are very lightweight elements compared to iron and silicates, which is what the Earth is mainly made of. The Earth does not have very much hydrogen in it, certainly compared to Jupiter. Is there another question about? Sorry about if I haven't recognized some of your hands with this light. Okay, going on to the atmosphere of Jupiter, that very top layer, which is the only layer that the comet interacted with, it serves a good purpose to know ahead of time, or at least have an idea of what's there. Down here we have the temperature in the atmosphere. This is all the Jovian planets. Over here is Jupiter. 0 to 300 Kelvin. 300 Kelvin is about room temperature that we're sitting in. This is the altitude in the atmosphere. We pick an arbitrary point to be 0. This is increasing, going further out of Jupiter's atmosphere. This is going deeper down into Jupiter's atmosphere. This yellow line here is showing the temperature of the atmospheric gases with respect to altitude. So you can see that it's getting hotter as you go in further, cooler as you go out to the top, and then you hit what's known as a thermosphere, whose heat is controlled mainly by sunlight. The atmosphere gets pretty thick around here. The top layer, now there are several layers of clouds in Jupiter's atmosphere because there are several different materials which make clouds. We have an ammonia layer of cloud, and then we have ammonium hydrosulfide layer, and we have a water layer of clouds. Now these clouds, again, as with the interior of Jupiter, they're models from what we know to date. And I've already heard with the Galileo results coming back that we may be learning new things about Jupiter. Here's a picture of the Galileo space probe. It's a cartoon. It's an artist's conception of what it would look like if you could watch the probe drop into the atmosphere of Jupiter like it did a month ago. Talk a little further out in Jupiter. Jupiter has an enormous magnetic field. This slide shows a composite and a comparison between the Earth's, Jupiter's, Saturn's, and Uranus's magnetic fields. An interesting thing to point out is with all planets, this is the rotational axis of Jupiter. The magnetic field axis, however, has a tilt with respect to the rotational axis, just as we have with the Earth. One of the beautiful processes that happen with magnetic fields is aurorae. We see aurorae, or the northern lights, on the Earth. And this is a picture of aurora in the northern magnetic field of Jupiter. Okay, now that I've gone through introductions, I'd like to talk a little bit about the discovery of Comet Shoemaker Levy 9. The slide here is the discovery picture of Comet Shoemaker Levy 9. It was discovered on March 24th, 1993, about a year before it collided with Jupiter. Who are the people who discovered this comet? You can know the name, you can know who discovered a comet by the name of the comet, Shoemaker Levy 9. It's the 9th comet co-discovered by a comet team made up of Eugene and Carolyn Shoemaker and David Levy. This is a picture of David Levy advertising a telescope in Sky and Telescope. David Levy is an amateur astronomer and an author, and he's discovered 21 comets by being very disciplined and looking constantly. Carolyn and Eugene Shoemaker are husband and wife, professional team that professionally are always looking for comets and near-Earth asteroids. They're staff members of the Lowell Observatory, and they've discovered 32 comets and 300 asteroids, 40 of which were coming close to the Earth. Now, to discover this picture that I show you up here was made with a 0.4 meter telescope, so a fairly small telescope that looks at a wide field of the sky. It's located on Palomar Mountain in California. The discovery was purely serendipitous. They've been doing this survey looking for near-Earth approaching asteroid for years, and in the process they find lots of comets. And when they saw this, they were very amazed, because as you can tell, just think back when I was showing you those pictures of Comet Halley. We had a large coma, one large coma and one tail. Here we have a very squashed looking comet, and the tails are extending from end to end. Closer views with the Hubble Space Telescope reveal a string of pearls, not just one comet nucleus, but 21 comet nuclei. Two other unusual things about this comet. One is it only has a dust tail. There wasn't any gas noticeably detected on it. Perhaps the gas disappeared. The other, perhaps more stunning aspect about this comet was that it was not orbiting the sun. It was orbiting Jupiter. Down here we have the orbits of the Earth around the Sun, Jupiter around the Sun, and here's the comet orbit around here. In larger scale, here we have some of the dates associated with the comet. It was found out within the month after the discovery of the comet that it was going to crash into Jupiter the following July 1994. Now, the orbit of the comet was also unusual in the sense that the orbital plane of the comet was not in the same orbital plane that Jupiter revolves around the Sun, which is shown here in blue. It was actually orbiting out of the plane, jutting down below the solar system plane, and orbiting Jupiter. Now, what do we think is the history of this comet? We think that around July 1992, the comet had a very close encounter with Jupiter, so close that it basically was torn apart in a tidal disruption. Now, what holds a body together? Usually self-gravity or tensile strength of molecules. When a liquid body, like a comet, can be approximated as, is near a second gravitational body, it gets elongated. And just as the moon induces tidal forces on the Earth causing tides on the Earth, Jupiter as well induced a tidal force on this small comet. And basically what a tidal force is it pulls harder on the side that's closer to Jupiter than it does on the part that's further away. And basically the differential gravitational force just stretches and shatters the comet. And we believe that's why what used to be one comet nucleus around 10 kilometers was shattered into 21 pieces of 2 kilometers or less in size. Now, these pieces slowly moved apart over time. Here's a picture shortly before. Sorry, this is a picture in 1993, shortly after the discovery, and they named all the pieces of the comet by letters of the alphabet so they could keep track of them. And these same letters were used to identify the impact sites on Jupiter. Over time, even these pieces disintegrated. This is the brightest part of the comet. It divided into 2 pieces apiece, and some of the smaller pieces even shattered down into dust, which just floated away. So there was a lot of time evolution here. Now, meanwhile, once it was discovered that this comet was actually going to crash into Jupiter, the whole world mobilized. Astronomers and telescopes around the world were pointed towards Jupiter to capture this amazing event. 2 spacecraft, the Hubble Space Telescope, of which many of these pictures that I'm showing you are from, participated heavily in this, and the Galileo space probe, which was just making its way to Jupiter, actually had a very stunning sight of the impacts. What was disappointing for astronomers was to find out that the impact site was going to be on the dark side of Jupiter. That is, we would not be able to see directly where the impact was going to occur. Galileo had a very clear view of the impact here. This limb here, this dividing line here is known as the terminator from the sunlit side and the dark side of Jupiter. Fortunately, Jupiter rotates very rapidly, and it was predicted that 20 minutes after the collision, Jupiter would rotate so that the impact site would come into full view of the Earth. There's a lot of speculation about, well, would this be exciting or not? And there were scientists on both sides saying, well, no, it's going to be a dud. No, it's going to be really spectacular. However, scientists mobilized nevertheless because such an event happens once in a millennia. And if you don't prepare to look and capture this data, you missed it. So the whole world mobilized, hoping that they were going to see something spectacular. And here are a group of astronomers at Space Telescope Institute anxiously awaiting that first results from that first collision on July 16, 1994. And they were not disappointed. This is the first image that they saw. This is from impact fragment A. 20 minutes after it collided, you can see a very noticeable ring and a dark spot at the center. These black bruises were seen from just about every impact site on the surface of Jupiter. Another common feature that was seen was, this is the limb of Jupiter, was to see a white light, mushroom cloud type feature rising above the limb. I want to show you sort of a picture show of some of the destruction that was seen, and then describe a little bit about what we think, the physics behind what we saw. Okay, this is a composite picture of infrared light from Jupiter. This is what it would look like if you could actually view from the south polar region of Jupiter. The collisions happened at 44 degrees latitude south in Jupiter, and so everything was down almost at the poles. To quote one astronomer, this is a necklace of impact sites created when that string of pearls of comet wrapped itself around the southern hemisphere of Jupiter. Now, the infrared light, what infrared shows is very hot. It shows the heat of the impacts, and you can see that the impact sites were a lot hotter than the normal quiescent rest of Jupiter. This is a visible image that you all have a copy of in your packet, showing that in the visible, what you saw was not bright spots on Jupiter, but you saw very dark spots. Astronomers think that this is sort of a soot that was formed on the surface, which blocks out the visible light from underneath. And in the ultraviolet, these dark spots show up even more grossly down here at the southern hemisphere. These letters, again, are identifying which comet fragment created which impact site. There is lots of evolution of the impact sites. This is impact site A, just 5 days later. And this is a time-elapsed photography of showing what happened to impact site A over time. You can see that it starts off as a nice sort of cohesive structure, and slowly Jupiter's very fierce 700 kilometer per second winds tear apart evidence of this impact site. Okay, another question for you about impacts. Why don't we see impact craters on the surface of Jupiter like we do on Earth? Why don't you talk to your neighbor again about this and then get your feedback on what you think causes that. Okay, let's pick someone over on the left here. This left section, let's see, one, two, three, 4 rows back in the jeans and a blue t-shirt, I think. What did you all think? What's the reason why Jupiter doesn't show an impact crater? Precisely. Jupiter is made of that very fluffy stuff. And in fact, the comet only hit in the atmosphere. There's nothing to kind of leave an imprint on. It's not a hard surface. It's very, very soft. And even this imprint that it makes, first of all, is torn apart by the fierce atmospheric winds. Okay, now let's look a little bit more closely at one of the impact sites, and then maybe describe a little bit physically why it looks how it looks. Okay, here's the impact site, G, in a very wide field image. Here's a close-up of that site, both in green light and in a line of methane. Methane's very, there's a high population of methane in the atmosphere of Jupiter. I want you to note a few structures. First of all, we have this dark thin ring, and inside this dark thin ring, we have sort of the streak of material. It's dark here, it looks light here. Outside the ring, we have this enormous horseshoe-shaped, kind of broader looking structure, and then we have a dark spot over here. What are these features? The small dark spot over here was actually caused by the impact site of fragment D, which occurred the day before fragment G happened, and fragment D was smaller than fragment G. So fragment G has a larger devastation, as we noted with kinetic energy. The ring, this very thin ring, we believe is a shock wave that's propagating out from the impact site itself here. And this dark streak, we believe, shows the trajectory at which that fragment G entered into the comet, into the atmosphere of Jupiter. So here fragment G entered from the south at about a 45-degree angle with the cloud tops of Jupiter, and that's why it's at a slant going in. And then this large horseshoe-shaped feature is some resettling material from the fireball that I'll describe in a moment. Now I'd like to show an animation it was actually a prediction of what would happen in the case of Jupiter. Okay, what we're going to see here is Jupiter. This small spot in the center here is where the impact site occurs, and these waves emanating out from Jupiter are the shock waves that are actually, we see only this thin ring here, but we believe that they propagated all over the atmosphere of Jupiter. Now, out of these reams and reams of data, astronomers hope to learn about the interior structure of Jupiter from these images of shock waves. Just as we use earthquakes on Earth to learn about the interior structure of the Earth, astronomers hope to use these shock waves caused by an impact, which is like an earthquake on Earth, and its shock waves propagating to learn actually some real facts about the interior structure of Jupiter. While this is finishing up, I want to, first of all, are there any questions? Well, we think this thin ring may be one of those waves, but these other waves that are seeing, there was thousands and thousands of pictures taken in the infrared, which is most sensitive to this reverberation. And it's going to take a couple of years of analysis to see if we saw anything worthwhile. Yes. Well, it would be nice if we could see it around the whole planet. Yes?
On one of the earlier pages in the handout,
Oh, okay. A complex crater is formed when you have a more massive impact. You notice the ejecta blankets created from the release of material from the impact, basically rebounding out. In a complex crater, you also have a very massive, when it's even a more massive impact, some of that center material also rebounds and just makes a little mound at the center. Okay, I want to move on to this fireball. This next video that I'm going to show, I'm going to talk while it's going on, is a numerical simulation of what would it look like if you could actually see the comet enter Jupiter's atmosphere. So what we have here, this stream going in here is the comet, and these layers, as we're going from right to left, are going from a less dense region of Jupiter's atmosphere to denser parts. Now what happens when the comet enters Jupiter's atmosphere is it's traveling faster than the speed of sound at 60 kilometers per second. And the frictional heating of the comet against the atmosphere actually heats up the atmospheric molecules, and it heats up the comet. In fact, it's going so fast, a shock wave develops, and it rebounds in Jupiter's atmosphere, as we saw in the previous video, and that shock wave also rebounds back on the comet. And what we're seeing in this video is when that shock rebounds back on the comet, it actually destroys the comet. It shatters the comet. It creates a very hot, high-density plasma. Now, this hot, high-density plasma wants to explode, but it explodes in the path of least resistance. Down here, we have more dense material, and off to the sides, we have higher density ambient Jupiter atmosphere. The easiest thing for it to do is just to shoot back along its entry path and blossom out. So basically, the comet goes down, gets destroyed, and then it gets shot back out. The pieces of comet plasma and atmospheric plasma get shot back out of Jupiter's atmosphere. It rises high above Jupiter's atmosphere, creating this fireball that we see. Now, this blossoming plume here is analogous to what you see in the mushroom cloud of fission bomb explosions. And if you look at pictures from the Hubble Space Telescope of that fragment G impact, this is what they saw at the very limb of Jupiter. So even though we couldn't see the impact site, that mushroom cloud, that explosive cloud, that fireball loomed so high above the limb, you could actually detect it. It just shot out of Jupiter so far you could actually see it, even though we couldn't see the impact site directly. It was just really very marvelous. It was sort of the best case scenario that they had hoped they would see, but they weren't sure they would see it because we still don't understand Jupiter's atmosphere all that well. So this white spot that we see here, and we're seeing in numerous of the collisions, is actually this fireball being lit up by the sun. Now, how far into the atmosphere did the comet get? That was something that was of deep importance in understanding collision processes and also understanding the atmosphere of Jupiter. In this schematic here, what I show are those atmospheric cloud layers in Jupiter I talked about earlier: water, ice, ammonium hydrosulfide, and ammonia. And this is the fireball explosion. We believe the comet reached down to the interface layer of the water cloud layer and the ammonium sulfide layer. Now, why do we believe that? I mean, certainly, even if we had a direct viewing of the impact site, which we didn't, we couldn't see down into the atmosphere of Jupiter to actually get a slice of seeing how far it went down. What we rely on is spectra of this fireball cloud and looking at the composition of the material in there. A lot of the spectra in the infrared showed us that there were evidences for water vapor, and we believe water vapor could only come from that cloud layer that was deep down. In the ultraviolet, we saw lots of evidence for sulfur-bearing molecules, molecular sulfur itself, and then a mixture with carbon, and that gave some credence to the fact that there's this ammonia sulfide layer. These layers are so deep down that you can't normally detect these layers of Jupiter's atmosphere. They were just surmised from models. So those people who model the atmosphere of Jupiter were very reassured to see that, in fact, there was water and sulfur down at the lower levels. Finally, one of the last aspects of this phenomena that we know now of what happened has to do with the magnetic fields in the dust. Now remember, Comet Shoemaker Levy 9 was disintegrating throughout its lifetime, and even during its final orbit to crash into Jupiter, those 21 chunks, some of them were disintegrating down into pure dust. What happened to that dust? Did that dust have any impact on Jupiter? In fact, we believe it did. This is a picture in the ultraviolet, taken of Jupiter to look at the aurora action. What we have here, these lines are actually drawn in. They weren't seen in the ultraviolet. They're drawn in to guide your eye to show you where the magnetic fields are located. What we believe happened is that dust came in and got charged, or made from basically charged particles accelerating in the magnetic field of a planet. And so these dust grains got charged, or in some fashion energized the electrons that are roving around Jupiter to create stronger aurora, not only in the southern hemisphere, but the northern hemisphere, indicating that there was some sort of travel path along the magnetic field lines to the northern hemisphere. These aurora were not only very strong, but they were seen down to unprecedentedly low latitudes on the planet. That's a little bit of what we understand happened during the collision. There's still reams of data to go through, and planetary scientists and astronomers will be working for several years trying to uncover deeper mysteries about the planet Jupiter. This event also sent reverberations throughout human society. We were all reminded that of the fragile environment that we live in today, and how nature doesn't always conspire to keep us living, but it's something we have to understand and be able to deal with. And I will leave you with some, I think you have this in your packet, some suggestions for further reading. My own talk itself, since I'm an amateur at this, I took mostly from numerous worldwide web pages, which I list here and acknowledge. Thank you.